Quantum circuits, how to build your first. Imagine creating a tiny machine that can perform calculations using the strange rules of quantum physics. That's what building a quantum circuit is all about. First, you start with qubits, which are the basic units of quantum information. Think of them as the quantum version of bits in regular computers. Usually, you initialize your qubits in the state called 0, which is like turning on a light switch. Next, you add quantum gates. These are special operations that change the state of your qubits. The most common gates are the Hadamard gate, which puts a qubit into a superposition, and the Pauli-X gate, which flips the qubit from 0 to 1 or vice versa. You can also use controlled gates like the CNOT gate, which entangles two qubits, meaning their states become linked. To build your first circuit, decide how many qubits you want to work with. For beginners, 1 or 2 qubits are perfect. Then, apply gates to these qubits in sequence. For example, you might start with a Hadamard gate on the first qubit to create a superposition. After that, you could add a Pauli-X gate to flip its state. These gates are represented as blocks on a diagram, flowing from left to right. Once your gates are in place, add measurement operations at the end. Measurement collapses the quantum state into a classical bit, giving you a result you can interpret. This step is essential because it tells you what the quantum computation produced. You can build and test your circuits using tools like Qiskit from IBM or Cirq from Google. These platforms let you create circuits by defining qubits, applying gates, and running simulations. You don't need real quantum hardware to see how your circuit behaves. The simulators show probability distributions of outcomes. Understanding that each gate corresponds to a mathematical matrix helps you see how they change the qubits' states. The order of gates matters because matrices do not always commute, meaning changing the sequence can lead to different results. Starting with simple circuits helps you grasp core concepts like superposition, entanglement, and interference. These are the key phenomena that make quantum computing powerful. As you get more comfortable, you can explore more complex circuits involving multiple qubits and error correction techniques. To sum up, building your first quantum circuit involves defining your qubits, applying gates to manipulate their states, and measuring the results. Using simulation tools makes this process straightforward and fun. This approach aligns with quantum information theory, where circuits representing algorithms that process quantum data. As you practice, you'll see how these tiny machines can do things classical computers cannot.